Yeah. Well, good morning, everyone. I hope you're all wide awake and ready for another round of sessions. So, what if we could actually catch a falling star, not just observe them from a distance, but actually be able to look at them up close and study them? When small meteoroids enter the atmosphere, a small portion can survive the ferocious entry and then gently rain down towards the Earth's surface, where we actually can collect them and study them. So this talk is about the search of cosmic dust on Earth and the story that it tells us about the chemical diversity and the evolution of the solar system. My name is Guido Jonker. I come from a geological background. I studied my bachelor's in earth sciences back in 2017 at the Vrije Universiteit in Amsterdam. And then after that, I did my master's in earth sciences as well. And I focused primarily on the geology and geochemistry of deep earth processes. And during my master's, for my research, I got involved with the work on micrometeorites, and I worked first on developing new extraction methods to collect them on rooftops. And then I also did oxygen isotope analyses to kind of study their origins. And as of last year, I am continuing my work as a PhD student, working with new kinds of samples to study the flux of cosmic dust that reaches the Earth. And so the main overarching goal of my research is to determine what that cosmic dust flux towards the Earth's surface is composed of in the first place. And then by studying several samples from various geographical locations and different ages, I try to determine whether that flux has been changing over the past few million years or not. In order to do so, we need to minimize the sampling biases so that all the collections, most accurately represent the true flux. And then by combining various isotopic analyses and targeting unidentified signatures, I try to get the most complete picture possible. So before I get into my research, just some general background. We live right here in the solar system. There's the main asteroid belt that contains the majority of the asteroids. And then further out are the comets in the Kuiper belt and the Oort cloud. But of course, we all know there's a lot of near-Earth objects as well, both asteroids and comets that contribute to the total number of parent bodies. There are two main mechanisms in which dust can be produced. So for asteroids, it's collision. So when two asteroids collide, they produce a vast majority of small dust particles. For comets, it's ablation. So when they come near the sun, they ablate their ice, and that ejects particles from the nucleus. As you know from Paul's talk on Friday, there is also human interference. So the DART mission produced dust that might reach the Earth as well. But the contribution of that to the total flux is probably negligible. So it's not that significant. The question whether asteroids or comets are the main source of most of the micrometeorites that we find on Earth is still a major topic of debate, to which I'll come back later. So once these particles are released from their parent body, they drift through the solar system on orbital trajectories that are roughly, in the same plane of movement of the planets. But they are affected by PR light drag. So as they move, their relative velocity to the speed of light causes aberration of the sunlight. So there's anisotropic re-emission of light, causes particle to gradually slow down and spiral inwards towards the sun, where they can be captured by the gravitational field of the planets and then accrete onto those planets. Together, because they move through the system, they're also called interplanetary dust, and they form what we call the zodiacal cloud, and that can sometimes be seen as a pillar of light rising from the horizon. And that's simply the dust reflecting the sunlight back to Earth. When they enter the atmosphere, they decelerate at altitudes typically between anywhere from 60 to 100 kilometers. And it's been estimated that annually about 30,000 tons of cosmic dust enter the atmosphere. But as you can see, they're quite rough estimates. But to daily flux, that corresponds to about 100 tons a day. And other estimates also imply that about 90% of that mass burns up in the atmosphere. But there is a significant portion that still can survive the entry. And that equates to about point is something in the order of 0.01 grams per square meter per day. And that equates to about 1 micrometeorite per square meter per year. So that is quite significant, actually. Well, depending on the several factors, these micrometeoroids ablate in the atmosphere, and that the mass that is ablated depends on several factors, including primarily the velocity, the angle, and the size. Typical asteroidal dust has velocities anywhere from 11 to 16 kilometers a second, and that's quite favorable for survival. But as you can see, if it increases, so here is the percent of mass ablations on the y-axis, and the horizontal axis is the size of the particles. So as the velocity increases, the amount of ablation exponentially increases. Same goes for the angle, so it's relative to the zenith, so the vertical. The higher the angle, the more favorable it is for the particle because it has a more gradual deceleration in the atmosphere. So its chances of survival are much higher. And then the size, typically these dust particles are up to 2 millimeters at most, but the majority of them are less than 0.5 millimeter or 500 micrometers. And in the same way, it rapidly increases. Depending on the peak temperature reached during that atmospheric entry, as well as the pre-atmospheric texture of the particle, they can create different recrystallization textures in the atmosphere. So at kind of the low end of the temperature spectrum, at somewhere in the order of 13 to 1400 degrees Celsius, they form what we call coarse-grained or scoriaceous. And these are in the process of devolatilization of their volatile elements. So they contain a lot of vesicles, and they also retain a lot of their original texture and mineralogy. Then at the higher temperatures, they form what we call porphyritic olivines. These contain large crystals, euhedral crystals of olivine. Those are followed by the barred olivine. Those are more platy, tabular-like crystals of olivine that are stacked on top of each other. Then at even higher temperature, they become cryptocrystalline. So these are like fine crystallites of olivine type crystallization that rapidly grows throughout the particle. Then at even higher temperatures, all the nucleation sites are destroyed. So it's hard for them to start crystallizing, and so they often quench as glass. That's typically in the range of around 2000 degrees Celsius. Then at even higher temperatures, although these are quite rare, we found what we call cat spherules. These are enriched in the refractory elements calcium, aluminium, and titanium. And these have ablated a majority of their mass. And so they also lose all of their iron, they turn completely white. These are quite rare and typically form at temperatures of about 2800 to 2800 degrees Celsius. Those all belong to what we call the S-type, so the stonies. They're chondritic in composition, dominated by magnesium, silicon, oxygen, those kinds of elements. Then there's also the I-type and the G-type. The I-types consist of iron nickel metal in the form of wüstite or magnetite that oxidizes in the atmosphere. The G-types are a bit of a weird group. We're not sure exactly how they form, where they come from, but they consist of an intermixture of a lot of metal, iron and nickel, as well as some silicate portion that is intermixed in the particle. Well, micrometeorites have been collected ever since the 1870s, but the research field didn't rapidly expand until the 1980s, when new technologies were developed and it became easier to study them. They've been collected from many different kinds of environments, including the stratosphere, with either collectors on airplanes or using balloons. They've been collected from deep sea sediments, from Antarctic deposits, as well as Greenland and also hot deserts. The benefit from these kinds of environments is that the particles are the micrometeorites are quite concentrated among the terrestrial particles. But the downside is that because of their age, they're often weathered accordingly. So they are highly altered, and that makes them less useful for isotopic analysis, for example. And in addition to that, the accumulation period is quite poorly defined. So it's hard to do like flux estimates and determine how much actually falls per year. Then since about 2017, people are actually finding micrometeorites on rooftops as well. And it's a kind of new development within this field, and it's also rapidly growing because it's quite fast and affordable and also really doable by citizen scientists. So even all of you here, if you have access to a microscope and some basic tools, you can even do it at home. And the rooftop, of course. Yeah. I'll have a list of basic necessities later. However, the big problem here is that you have to deal with a vast amount of contaminant particles, not only from terrestrial sources, but for a large part also from human sources. And that is the major challenge in training your eye to distinguish the two and really, make sure that you're finding micrometeorites and not anything else. So far, there have only been a handful of publications on this topic. So it's a really new, interesting, developing field. So I set off to continue this kind of work. So I collected a massive sample from the gutters. I emptied it on both sides of the barn. And I sampled it twice over a period of 3.5 years. And in total, I collected about 70 kilograms of raw material that I had to process. So it took a lot of time, but I managed to find just over 1,000 micrometeorites from that one sample. And to date, that's still by far the largest collection from a single rooftop. So that gave us a lot of insights into, what falls at the present time, not just as an average over the couple past million years, as in many other samples, but really what is falling right now. So to get from 70 kilograms down to 0.01 grams total of micrometeorites, that of course takes some processing. So people usually use magnets, which works decently. I mean, you can extract the majority of them, but I wanted to minimize all those biases. So instead, I focus primarily on the shape and density. So what you see here is what we call a foul table. It's a pitched vibrating plate that separates particles based on their sphericity. And then I collected those spherical fractions and I continued working with that. And then I took it to the centrifuge. It is a fast spinning cup that contains, you pour heavy liquid in there, and depending on the density of the liquid, you get a separation between a float and a sink. So you can actually quite accurately and quickly separate them. So I concentrated them in the heavy fractions because of the composition. They're relatively heavy compared to at least most terrestrial particles. And then for some of the smallest fractions, I still needed to do some magnetic extraction as well in order to concentrate them even further. And then it's off to the microscope for hours, days, and sometimes weeks on end of microscopy to isolate the particles among all the other ones. So these are micrometeorites, and then I bring them in for the electron microscope, and then we can actually image them quite nicely and in high resolution, and also analyze their composition to really verify the origin. Here are some color images of some micrometeorites from this collection that were photographed by a friend of mine. The poster is on the table as well. And there's a couple of particles, these two, as well as this one and this one, that are under the microscope. So if you haven't seen them yet, go have a look afterwards. So that was all primarily still part of my master's research. Now I'm working with samples that come from Wallenfjellet, which is like a nunatak, a mountain in Antarctica, as well as a sample that's been collected in the Catalina area of the Atacama Desert in Chile. And the exposure ages of these outcrops has been estimated to be in the order of about 1.7 million years for Wallenfjellet. And it could be up to 6 million years or more for Catalina, but they only sampled the top layer of the soil, so it could also be quite recent instead. We're not entirely sure about that. A lot of people of you have been asking me already, like, what's the size of these particles? And there's been a lot of discussion about these because various studies have found quite different results. But the results of my work align quite well. So we see a major, this is the size frequency distribution. So the number of particles in a certain size fraction. And so you see these peaks right about 100 to 130 micrometers. So that's where they primarily, focus, but they range anywhere from 50 to 250. That's usually where the bulk of the particles is. they can get as small as 30 microns and as big as a millimeter almost. So there's quite this large range, but if you're going to search for them yourself, make sure you focus on this kind of size range primarily. So to give you a visual idea of what that looks like, here's a particle on my fingertip that's actually still a relatively large one. I believe it was about 400 or 450 microns or such, so it's on the high end. The one over here is not to scale relative to that one. This is the largest I found of about 750 micrometers. That one is one of the smallest at only 30 microns. So you see there's quite a large range of sizes. And then another big discussion has been on the relative abundances of these different types. So the porphyritics, the barred olivines, the coach crystallines and such. What people have been doing is making statistics of the percentual abundance of each type and presenting that as a table like this. As you can see, that, for example, the porphyritic olivines is a massive range in their abundances, similar for the I and G types combined. There's really no consensus on this yet. And what people are concluding from this is that probably, the flux must be changing over time and depending on different movements of the planets and such, that over time, the entry speeds and angles and such of the particle changes, and so the textures do. But what I'm finding now, because I'm using consistent methods and consistent classification, separation methods, the Guido collection, I know it's biased because it's really difficult to work with rooftop samples. So we're not finding any of those I, G, and cat type spherules. It's just almost impossible. So if we take that into consideration, it's still quite comparable to the new Catalina and Waldenfjella collections. And interestingly, these two are nearly identical. Locations, different ages, different environmental conditions with weathering and such, but still there are barely any differences among them. And so what it implies to me, at least, is that the majority of these previous results are biased either due to different collection methods or separation steps, even the classification, which is kind of subjective to human bias as well. If we get rid of most of those biases, all these differences kind of seem to disappear, and that again then tells us that the flux as a time average must be relatively stable. So what falls now has been quite similar to what's been falling for the past few million years. Well, then I also did the oxygen isotope study. This was on particles from the Guido collection. We analyzed 80 in total. I know this is a hugely complex figure. I don't need you to understand it entirely. What you just need to understand is that these clusters are carbonaceous chondrites, larger meteorites that have been analyzed. The blue ones are ordinary chondrites. That's like the bulk of meteorites that we find. Typically, the larger meteorites that we find all belong to ordinary chondrites. But for the micrometeorites, about, at least in our population, about 71% of them all belong to these carbonaceous chondrites. And they plot outside of the field, and that has to do with the ablation in the atmosphere. So it's easier for them to evaporate the lighter oxygen isotope than the heavy oxygen isotope. So they become passively enriched in the heavier isotopes, and so they shift horizontally in this diagram. But then what I'm currently primarily focused on is this cluster right here, because there's nothing here to correlate them to. But they plot along this line we would call the CM mixing line, which includes some of these carbonaceous chondrites here, the CM group, as well as the CY. So the good idea is that they may be an extension to the CY group, but at heavier values. And so they experienced a period of aqueous alteration on their parent body. That's what we know so far. And based on the texture that some show, like these cumulate stack texture, we can reconstruct their entry parameters. And so we know they have relatively high entry velocities compared to the other particles that we find. And so far, it's been related to a possible near-Earth object, maybe CY Chondritic asteroid. And what I'll be trying to do is use silicon and iron isotopes on these particles and combine that with trace element composition. So the elements that are in really, really low abundances in these particles, but they are like a fingerprint for their origin. So hopefully with that, we can confirm and relate them to CY chondrites and see if that matches. If not, we still need to keep looking. So it's going to be an interesting find. And it possibly tells us more about the solar system and the total diversity of objects is out there. That still leaves us with the question as to whether most micrometeorites originate from asteroids or comets. And it's been a major topic of debate. And there are various arguments, counter arguments. So a lot of people say like the dust production mechanism of asteroids is more favorable because if they impact, they create such vast majorities of particles. But then on the other hand, a lot of numerical models are suggesting that that zodiacal cloud is mostly consistent of particles that originate from comets. And then the other group again says that survival of asteroidal particles is much more likely simply because their entry speeds are much lower, so they're more favorable to survive in the atmosphere. But those same models are again telling us that the speeds of those cometary particles can probably also, for a large part, be similar to these asteroidal particles, so they're just as likely to survive, maybe even more likely because they have relatively low densities. So that also favors their survival. Then when we make polar sections of these particles, we find specific minerals, which are hydrated phyllosilicates. And what we know from the samples that we've returned from asteroids and comets, these are quite common in asteroid, but not so much in comets, at least not the samples that we've collected. So that points to asteroid. But then at the same time, we're not finding a lot of chondrules in these micrometeorites. And those chondrules are similarly rare in comets. So that again points to comets then. Well, from the oxygen isotopes, we know that the large ones are typically related to ordinary chondrites. So there seems to be like a consistent change from carbonaceous dominated micrometeorites to ordinary chondrite dominated larger meteorites. But then again, the small ones are not. But simply by telling that they're carbonaceous, we're not sure if it's asteroidal or cometary. And then, people are suggesting that the asteroids are simply more abundant in the inner solar system, so it only makes sense the majority of particles originate from those. But more and more results are indicating that a lot of those asteroids are more like extinct comets that only appear to be asteroidal, but might have the chemistry of a comet. And then you're probably all still wondering how you can actually contribute to this work yourself and how you can find micrometeorites. So I've made a basic list of the necessities that you need to start working on this yourself. First, for the collection, you need the rooftop. There it is. You need some basic brooms, brushes, a bucket and a bowl to just collect your sample. Some bags, some sieves, and a neodymium magnet, which works fine if you're just starting. Then for the actual searching parts, you need a microscope, preferably a stereo microscope with a proper light source, some dishes, a pix, a pin set. And for storage, it is useful to have capsules or glass slides and some double-sided Scotch tape to stick them onto. And the most important one is patience and persistence. Don't be discouraged if you don't find them the first try, not even at the 10th or the 20th try. You'll find them eventually. Here's a quick step-by-step guide. So first, find a suitable rooftop, preferably one that doesn't contribute to the sample itself. So anywhere with like these black bitumen rooftops, don't go anywhere near them. They're terrible. You don't want any contribution from the rooftop itself. So corrugated sheets, for example, are my personal preference. Then you collect the sample, make sure you get proper access as well from the owners. Wash and dry the samples until you're left with clean sand. Then you can sieve that material. You can use basic kitchen sieves for this as well. It works just as fine. Then you do the magnetic separation. If you can kind of simulate the shape separation. If you just have a solid sheet and any type of vibrating device held against it, you can kind of simulate this shape separation. And then you can do the actual microscopy and the archiving of your particles. So these are a couple of examples of good and bad samples. This is how I started. I said, don't go anywhere near them. These are terrible samples. With all these spherules are metallic particles that originate from the rooftop. You're not going to find anything in there. This was slightly better. I managed to find my first micrometeorite in here, actually. It was a glassy spherule, but still, these are not great to look for micrometeorites. This is much better. As you see, there's not really that many particles that look like these micrometeorites at the center. As a quick final warning note, these are a couple of examples from particles that are not micrometeorite, but really, really look like them. So this is just an example of the kind of particles that you can come across. So to conclude, what I found so far is that there's no major changes in the dust flux so far. It's dominated by carbonaceous chondrites, but the question still remains whether that is asteroids or comets. And the 1604 micrometeorites might define a completely new chondrite group, and thus we can learn more about the solar system in general. So with that, I'd like to thank you all. And if there's any questions, feel free to ask them.
Thank you, Guido. If we have some questions.
Very nice talk. Has anyone looked at like Antarctic ice cores to see if there's a change in the flux? Do you know?
They've looked at ice cores. Not any flux changes that I'm aware of, at least. There's one question. Oh, yeah.
Just a question about asteroidal source. In fact, you show big impact, but I think most of the incoming matter come from thermal fragmentation. And
yeah.
So, and maybe it's why you have so many chondrules. No?
Yeah, but for example, for the larger meteorites, a lot of the ones, the ordinary chondrites, they originate from one single parent body that was destroyed some 480 million years ago, I think. And that still contributes to the majority of meteorites. So it might well be plausible that it still contributes to the majority of micrometeorites of that type as well.
Okay. I was wondering, I didn't get why the sample from the rooftop was biased, and so you could not see the CAT, the cat, and
yeah.
I plus G. I didn't get that.
It simply has to do with what I've learned now is that they're typically relatively small, so anywhere below 100 microns. And most people start searching upwards from 100 or 115. I started at 90 microns because anywhere below that, you have so much sample to work with. It's just undoable to process it with such volumes of material. So then you're already losing 90% of them, and the other 10% is just really, really difficult to recognize among all the human-made particles.
Just you mentioned that you don't see chondrules much in comet dust, but I remember this mission from Weil 2.
Yeah.
I seem to remember that these dust particles contained a lot of chondrules, but maybe I'm wrong.
Some, I think, yeah. It's just that the abundance of chondrules that we find, especially there's also a group of unmelted particles in which we can find these chondrules. Their relative abundance of these chondrules matches with those kinds of results from those return missions. In a typical carbonaceous chondrites for asteroidal particles, it's ranges from 10 to several tens of % of particles, and that's simply not consistent with what we're finding in the micrometeorite. So yes, there are some in comets as well, of course.
Yeah, so if I remember correctly from atmospheric circulation, when you have these ablation remains in the mesosphere, a lot of them will be transported towards the poles before they sediment down. Would you find more of these near the poles than other places, or is it something you've been looking at?
That is also another question still that needs to be answered. Like, does the flux change geographically? We're not sure yet, but the evidence is not really suggesting that. It's suggesting that it's relatively stable across the globe, but there's major uncertainty, so it's really difficult to determine it.
One last question and we'll move on.
So you find that that there's been no significant changes in the flux over the past mega years, but would it also be practically possible to find a suitably large surface that you could really sample, you know, on a very regular basis throughout a year, or do that for several years, to see if you can discern annual patterns in the flux, and thereby connecting the flux to swarms, for instance?
Theoretically, yes, that's of course really possible, and there could be a relation to meteor showers, but then the entry speed of those meteor showers is likely too high to survive the entry. So you can sample around meteor showers, but you're probably not going to find any of those particles. So it's kind of the more of the background signal probably that what we're finding. So personally, I don't think that on a monthly or annual scale there's that much variation really in what falls to the surface. It is possible to do this kind of work, but it takes so many years, so much work, so much processing, and then still the uncertainties are really large. So it's really difficult to do that.
All right, let's then Guido one more time.